Here is a sentence that ought to be strange, and isn't, because you have never had occasion to notice it. The numerals you use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are called Arabic. They are not Arabic. They were invented in India. Arab and Persian scholars adopted them, improved the arithmetic that ran on them, and wrote the books that carried them west. Europeans, meeting them through Arabic sources, named them after the messenger and forgot the sender. The most universal notation in human history, the one thing genuinely shared by every culture on Earth, present on every price tag and passport and phone screen, from Reykjavik to Jakarta, arrived in your hands under someone else's name. That mislabeling is the story of this part of the book in miniature. For roughly 17 centuries, the great work of mathematics happened almost entirely outside Europe, and Europe eventually inherited it without quite understanding where it had come from. The version most of us absorbed goes something like this. The Greeks invented mathematics. Rome had other priorities. Then the lights went out for 1,000 years, and the Renaissance switched them back on. Nearly every part of that is wrong, and the part about the lights is wrong in the most interesting way. The lights did not go out. They moved. The Romans, to be fair, really did have other priorities. They were magnificent engineers and organizers, and had almost no interest in mathematics. As a subject in its own right, Cicero was prouder of finding Archimedes' tomb than any Roman ever was of proving something. But the far larger point is that Rome was never where the action was going to be anyway. While Europe was busy having what used to be called the Dark Ages, the intellectual center of the world sat comfortably elsewhere, and stayed there, and did not consider itself to be waiting for anyone. In China, mathematicians were solving systems of linear equations, with a technique that would be rediscovered in 19th century Germany, and named after Gauss. They were doing arithmetic with negative numbers, casually as a matter of course, using red and black counting rods, while European mathematicians were still calling such quantities absurd and fictitious, 1,000 years later. In India, astronomers and mathematicians took the blank space that Babylonian scribes had lived with for 2,000 years, and did the thing nobody had done. They made it a number. 0. Not a gap. Not a placeholder. A quantity with rules that you could add and subtract and multiply, and dangerously attempt to divide by. And in Kerala, in the south, mathematicians would eventually sum infinite series to compute pi, arriving at results that Europe would not reach until Newton's century. And in Baghdad, in a burst of institutional ambition that has few parallels in history, a dynasty of caliphs went looking for every book in the world. Greek, Persian, Indian, Syriac, they bought them, seized them, demanded them as terms in peace treaties, and paid translators handsomely to render them into Arabic. What was assembled there was not a museum. It was a working laboratory, and out of it came a genuinely new way of thinking about the unknown. A method for handling quantities you do not yet know the value of, which its author called Al-Jabr, and which we call algebra. His name, worn smooth by Latin transliteration, is the word we now use for a step-by-step procedure. Algorithm. So the title of this part is meant literally. The numbers traveled physically along trade routes and pilgrimage roads and the paths of armies, carried by merchants who needed them for accounts and astronomers, who needed them for calendars and translators paid by the page. And in traveling, they changed. This is the second thing worth watching for in the chapters ahead. Mathematics is often described as if it were discovered in a vacuum by solitary geniuses. What actually happens in these centuries is that ideas cross a border and are transformed by the people who receive them, because those people want different things. The Greeks, wounded by the diagonal, had made geometry their foundation and treated number with suspicion. India and China had no such wound and no such inhibition. They were free to be bold with number in ways no Greek could be, and their boldness is exactly where zero and negative numbers come from. Baghdad received Greek geometry and Indian arithmetic in the same building at the same time, and the fusion of the two is what made algebra possible. Nobody planned this. It happened because a translation project needed staff. And when this accumulated inheritance finally reached Europe through Spain and Sicily, where Arabic and Latin worlds touched, and through the notebooks of an Italian merchant's son who learned his arithmetic in North Africa, it did not arrive as a triumph. It arrived as a dispute. For 300 years, European merchants and scholars fought over whether to abandon Roman numerals and the counting board for these strange foreign digits. Cities passed laws against them. Bankers were forbidden to use them in their books, on the grounds that a 0 could too easily be doctored into a 6 or a 9. The people who wanted the new system were not philosophers. They were businessmen who had noticed that you could multiply with it. There is one more thread running through these 5 chapters, and it is the one this book is named for. Part 1 ended with a monster the Greeks had proved into existence, and then declined to invite indoors, an unspeakable length, walled off in geometry, never admitted as a number. Part 2 is about the arrival of 2 more monsters, and about civilizations that, for once, opened the door. The first is nothing. 0 is so ordinary to us that it takes real effort to see it as an achievement at all. And yet, for most of recorded history, the idea that nothing could be a number was not merely unfamiliar. It was close to a contradiction in terms. A number counts things. What does 0 count? Making it a number required someone willing to say that the absence of quantity is itself a kind of quantity, and then to go further, to ask what happens when you divide by it, and to follow that question into the strange country beyond. The second is less than nothing. Debt is real. Everyone has always understood debt. But the notion that a quantity smaller than 0 deserves to sit on the number line alongside 3 and 7, that you can own negative sheep, struck most mathematicians who met it as obvious nonsense. Chinese calculators accepted them early and quietly. Indian mathematicians gave them rules. Europeans resisted them for 1,000 years and were still calling them false in the 17th century. Both would be absorbed. Both are now taught to 7-year-olds, who find them unremarkable, because that is what always happens. By the end of this part, the mathematical world will have 0, negative numbers, the decimal place value system, algebra as a systematic art, and a growing body of results about infinite series that ought to have led straight to calculus. It will also, in 1500, be poised to hand all of it to Europe at precisely the moment Europe develops the printing press. But first, we go east to a river valley in China, to a book assembled across centuries, and to a set of little colored rods that could do something no Greek would have permitted.